Okay, off we go. This is week 12, 12, 13, 14, 15. So just 3.5 weeks. That, of course, does not include Thanksgiving week. I have some questions queued up here, which I'm happy to answer. Any other questions before I take a look at that? Okay. Do I teach 211? No, I don't teach 211. Let me see. Your best place of catching me is in the 500 level courses. I teach 511 and 515. The next lowest course I teach, which I believe, if memory serves, is only requires 211, is 344, which is shell programming, where you learn basically everything that has to do with this command prompt and how to write scripts. For instance, mkdd is a little script I wrote that interrogates the current date and then changes into, in this case, the 111 directory and creates a directory with the current date and throws me in there. It'll do that for any class that I'm teaching. So that's what 344 is. You learn that. You learn about half the class is scripting related to this prompt, and the other half of the class is Python scripting. I do, however, the one caveat on that, which would turn you off probably, is that I generally teach that as a summer course. The summer courses are, at least the one I teach, is accelerated over 6 weeks, and I think that that is a perfect forum for 344, as opposed to stretching it over a semester, which I don't think is needed. So, no, don't teach 211. I don't know whether that gives you relief or not that I don't teach it. Will we learn Will we learn operator overloading in this class? It's not a 111 topic. I'm happy to give it a little bit of coverage just because it's fun, kind of scratch the surface of it. So maybe sometime next week. I'll leave that actually queued up. I might give that a gratuitous lecture. I think it's within reach of being able to play around with it. Will I be at Bidwell Perk this weekend? That's an excellent question. I don't know. Maybe. I can probably. I'll leave that queued up as well. I'll make a decision on that on Friday. So I'll answer that definitively on Friday. It would be Saturday morning that I would be there. So a definite maybe on that. I want to graduate already. Man, I hear you. I was so sick of school. But most of you, well, not most of you, about half of you are not freshmen because you're not in computer science, right? Sophomores and juniors. But yeah, I was sick of school. I hated school. So if you want to graduate, I understand. I sympathize. Just for your eye, Lab 21 is also posted for next Monday's lab. Yeah, so I haven't updated all the What's Due When stuff. I actually crammed a new lab in there that I thought about the last couple of days and wrote this morning while, incidentally, sitting at Bidwell Perk. So everything after week 11 on this thing's out of whack. Or excuse me, after week 12. So week 12 I just shoehorned in here. And this week 13, yes. So take that with a grain of salt. All this stuff changes. Ignore week 13. I'll get this fixed up a little bit over the weekend. But all you can rely on at this point is week 12. I have had some ideas on what to talk about today, so that's where this lab came out of. And then I have an assignment that is related to that will kick off on Friday. So my apologies for dropping the ball weeks out on the final weeks here. Mixing things up. There's that. Actually, what I ought to do, since hang on, week 13, edit. We'll put that there. All right. So that fixes that problem. Thank you for the FYI. What is a software stack? It's referring, there's more than one stack. It's generally referring to a suite of tools, an architecture, like you often hear the LAMP stack, LAMP, that's just an acronym for Linux. A is for Apache, which would be, it's almost guaranteed, I don't want to say almost guaranteed, the vast majority of the time when you're browsing a website, the software serving up that web page is probably Apache. It's definitely has the lion's share of web servers out there in the universe. So Linux, Apache, the M would be MySQL, or it's just referring to some database software, and then the P would be something like Perl or Python. So it's referring to kind of these disparate technologies that are generally grouped together to deliver something. So you often see software delivered with a LAMP stack. There's a different software stack for some other type of application. That's all that's referring to is disparate pieces of software that are lumped together because in combination they do a pretty good job at what they do. So that's what that is. All right, any other questions? Okay, then let's go ahead and kick off some new stuff. I wanted to introduce you to a bit more of the standard template library. You got some exposure to the standard template library. I guess I can reprise it just a little bit in the form of vectors. Oops. So you have to include vector, and probably the next thing you should do is type C++ vector. There are a couple good, there's many tutorials and so forth. As far as where I usually end up going is c++.com. And the format of it suits me well. So to be sure, c++.com is not a tutorial site. It's more of a reference site. But you can glean a lot of useful information out of it. Let me just give you the format of this. It's giving you a summary of what you're looking at the top of the page, as you would expect. For this thing as I would call it a type, I guess. These are all the things I can do with this vector. Let me blow it up here a little bit. And I'm pretty sure I visited this before. But even though it's not a tutorial site, you can get useful information out of it. And what I mean by that is, for instance, I'm kind of interested in this element access. So we know enough about vectors to know that you shove a bunch of stuff into them. And this square brace is what we've been using it intuitively for. So we've been doing things like vector. Here we have to provide what kind of thing we want to store in our vector, give the variable a name, and then we do things like numbers.pushback, numbers.pushback. Yes. So what I would do is I would look at this thing, and I would find Modifiers, pushback. Modifiers just simply means it changes, in this case, numbers. So pushback is one of the functions that changes numbers. And it means add a new element to the end of the vector. So the term back comes from the sense of, if you imagine, I don't know, you have a stack of plates and you turn that sideways, it has a concept of the front of that stack and the back of that stack. And so when you push back, you're adding another plate to the end of it. Or in my case, floating point numbers I'm adding. So let's see. There we go. Nope, I don't want to do that. What am I doing wrong here? I think that's fine. I'm going to do it that way. All right. Okay, so I got distracted in typing that out, but this is useful because although this kind of stuff may be a bit hard on the eyes, I can get some ideas of how to use it because invariably they provide some sort of example here. And you can see this example is relatively simple. Here I have a vector of integers, they call it my vector, and then they have a loop here, a do while to say please enter some numbers, 0 to end, and it's going to do it as long as my int is not equal to 0, inputs it, pushes it back, and then it prints out the number of items in the vector. And again, this was on pushback, so it shows you how to use pushback. So if you're wondering, well, how do you use this? How do you use that? Clicking on these things will usually give you a little example program that would show you how to use it. All right, so I wanted this is by way of introduction to say that vector is what is referred to as, I guess I'd call it a container in the standard template library. So standard means that every C++ implementation you come across is going to have it. Template is actually a technical construct in C++, and when you get to an advanced level, you can actually write your own templates. But colloquially, what it simply means is that you are allowed to specify what that thing works on. Meaning, in line 8 there, so someone out there, some software engineer, wrote this vector container, but they made it generic such that I can have a vector of floats, a vector of strings, a vector of knights, a vector of weapons, right? It can be a vector of anything you want. And that's kind of the joy of the standard template library, is they provide these kind of generic algorithms, these generic containers that do useful things that we need to do in the programming world, and we can go ahead and provide the types. So that's a template part, and then library, obviously, is what it implies. It's a library of these things that we have access to. So the one I want to introduce you to today is an unordered map. I'm going to call it. There's actually both an ordered map and an unordered map. If I was to use an ordered map, I would just say map. They don't use the word ordered. So by default, your map will be ordered. I'm specifically going with an unordered map. It doesn't really matter which I choose at this stage of the game, but unordered map would be a little bit more graceful for me to choose at this point. What a map does, whether ordered or unordered, is it allows you to map keys to values. What can a key be? A key can be an integer, a key can be a character, a key can be a string, a key can be a night, a date, You get the idea. This is a template library. The value also can be anything. And so we just have to ask what it is we want to map. So let's say I'm creating a code book and I want to map words to code numbers. Then I would say that I have an unordered map. And in the angle braces here, I have to provide two types. Note on line 8 on the left-hand pane, I only need to provide one type because that's all that's necessary to use a vector. In the case of any sort of map, I provide two. So I'm mapping strings, which would be words, and I'm going to map them to numbers, my code numbers. And I guess I'll call this the code book. Now I need to fill it up with items. And they make it very easy to do that. I can say code book, and I start adding. So for the string tomato, we'll make that equal to the number 394. And potato, this will be 48. There are quite a few words in the dictionary, so we'll be here a while. I'll confine myself to just a couple vegetables. Already done. Here I'm struggling to think of a third vegetable. Carrot, thank you. Yeah. I'd like every one of them to have 6 letters because it kind of lines up nicely here. This will be 2. Pepper. All right. Well, that'll be enough. And that'll be 99. There are I'm actually going to add a bit to this entries in my map. I'm going to come over here and compile it. One of the things we want to determine is whether an entry is in our code book, because obviously I don't have quite all the words in the dictionary there. So let me see. Let me say enter, how about cout, enter a word to code. And then I'll create a string. We'll call it word, thank you. If codebook dot count word, let me pause. Let me type unordered map here. Here are all the things I can do with my unordered map. And count. It says count elements with a specific key. My specific key here is the word that the user just entered on line 20. And they're using fancy dancy looping here. But here they're finding out how many items there are in there. There's either how many items could there possibly be? There could either be 0 or 1. Yes? Either it's there or it isn't. So if it is there, the code is, and then I will type, let me go ahead and make this full screen. Let me bring this so we can see it a bit higher up. The code is, and then it's codebook at. There are a couple ways of doing this. I'll show two ways of doing it. Else, no entry. So I'll put a little comment here. Count is equal to 0. Okay. So let's go ahead and take a look at that. Let me try making this. Enter word to code, FDSA, no entry in codebook, caret, tomato. Yes? Yeah, any number you want. I just made those up. And it doesn't have to be numbers, right? I'm just inventing this example out of thin air. The key takeaway is on line 8, I can have anything I want as the key and anything I want as the value. It's totally up to whatever your need is. Yes?
Maybe the same thing.
Oh, absolutely. Yeah. It can be string and string or int and int. Sure. Yeah. I just made it up. Right? I made up the words. If you don't like eating your vegetables, then you can choose different words if you like. All right. Okay. So that is, there's going to be a lab today. The new lab 21 is going to be using this unordered map. Oh, I said I'd show you a couple ways of doing this. The other way is, what I'll do is I'll just I'll do it a second time. So let me compile it. Let me run it. Tomato. So lines 23 and 25 are two ways of doing the same thing. I showed you line 25. I think 25 feels more natural. However, it's the one that I'm a little bit hesitant to show off because it isn't such a huge deal right now, but assuming you go on to say 211, this one comes back and bites you in the ass, because I'm very careful to only do line 25 if I've confirmed that that word exists in the code book, right? I did that on line 21. The only way I can hit line 25 is if line 21 is true. In fact, let me just make this a little more obvious. Equals 1. If it exists in the code book, then I'm going to access it that way. What would happen if it didn't exist in the code book? And the answer to that is just look at lines 9 through 12. If it doesn't exist in the code book, it creates an entry in the code book. And that's what I mean by it comes back to bite you in the ass. You may think you're looking to see if it's there, but you're not just looking to see if it's there, because if it isn't there, you're suddenly putting it in there. So be very cautious when you're using the square brackets to access elements. It's great for accessing them if they're there, but if you're not sure they're there, don't be accessing them that way. Instead, use the at version of it, because at will not add an entry if it's absent. Yes? How many items I put in the code book. So on lines 9 through 12, I put a total of 4 items in the code book, which is what you see on the top left pane. There are 4 entries in my map. That corresponds to the tomato, potato, carrot, pepper. Any other questions? Yes? So that function is specifically, what does it say? Count the number of elements with the specific key. So quickly looking at this, the specific key is in line 21 is word, which is going to be whatever I typed in. Quickly casting our eyes to the left pane, I typed in the word tomato. So in this example, it's giving me a count of how many times tomato exists in my map. And then if we look at the return, again, I'm looking at the reference page for the count function. The return value is count is going to return 1 if the key is found, otherwise it's going to give me 0. All right? So note that this is similar to, well, I don't want to go any further than that. So that's that. There are other kinds of containers where I can attach a bunch of things to a key, in which case count would be 0, 1, 2, or 3. But those are different containers, not this unordered map container.
So if you were to type in stuff like the codebook.com, if you were to hard code in some kind of word or like check and see if it was there, or if the user entered in a word that wasn't there and said that it was not in the codebook, does it will only add it if you
the only time you're going to add it is if you do something like line 25 and it's not there. Or obviously lines 9 through 12, if you do that, it will add them if they're not there.
yes, like if you didn't have anything else and you just put the codebook with the hard copy in the code, would that add it?
Absolutely. If you did line 25, actually I'm not sure. Let's see if it compilers. So let me go ahead and do this. If I type candy, then it did put the entry in there, but it basically gave a default value for the value portion, which in this case is 0. That's correct. So if we can go ahead and add down here. Oops, sorry, that's the wrong class. So again, what we're seeing is the danger that I was pointing out, which is on line 18, candy did not exist in the code book, but I unwittingly added it to the code book by virtue of looking for it using the square brace. Yes? They both look for so they're the same, and they both look for that word in there. The difference is on line 26, it'll add it if it doesn't already exist, which is what happened on line 18. Candy was added as a key to the code book. When just looking at line 18, you may not realize that, but that's exactly what it's doing. At is a safer version in the sense that it will not add it to the code book if it does not exist. Now that doesn't, but I'll broach the subject, but I'll get down the rabbit hole if I go too far. this isn't going to end nicely. Let me put it that way. So line 18 will not add candy to the code book. However, when I run the program, what I get is, let me bring this up. Basically, this uncaught exception of what it does is what I would term it throws an exception, and you can write C++ code to catch exceptions, but it's kind of an advanced topic. We don't really talk about exception handling or how to catch exceptions or anything like that. So the way I was able to finesse that in this discussion is that before I do anything with codebook, I basically do line 22 to find out if it's there. And only if it's there do I access the codebook. And that avoids all these problems. Yeah. So I'll go ahead and put this the way it looks. I'll do that and do that. Any other questions on that? Okay. Let me talk about a different topic. Oh, let's see. Okay, what I'm trying to start to show off here, I talked about this a little bit. You may have had this in some other computing class, but I'll give it a slightly more applied treatment. This is showing this is 2 raised to some power, and this is showing you how to calculate binary numbers. And people, for whatever reason, people have a hard time getting their head around this, but let's see, which way am I going? All I have to do is change that 2 to a 10, and everyone grasps this unquestioningly. So if I put a digit here, let me just do it this way. All right, so 10 to the 0 is 1. 10 raised to the first power is 10. 10 squared is 100. And this is 1,000. And then I'll stop here. This one is 10,000. So all you do is you take this number down here and you multiply it by this number up here, right? 0 times 1 is 0. 1 times 10 is 10. So let me write 10. 10. 0 times 100 is 0. 1 times 1,000 is 1,000. And then 1 times 10,000 is 10,000. And then if I ask you, what is that number? You just add them all together and you come up with 1, 1, 0, 1, 0. That's the process that we're doing. Although we've done it so frequently, we don't even think about it. I used 1s and 0s here, but in our numeric system, there aren't 2 glyphs to represent our digits. There are 10 glyphs, 0 through 9. And so I can put any of those 10 glyphs here. So I can put a 3 here, and I can put a 4 here. And then it's 4 times 1, 1 times 10, 3 times 1,000, right? And we go through the exact same process, and we end up with 13,000 14. It's the exact same process with binary numbers. So I can put a 1 here, I can put a 0 here, a 0 here, and we'll just stop there, a 1 there. I'm having fun. 1 here. All right. And then you go through the same process. What is 1 times 1? It's 1. 2 times 0 is 0. 2 squared is 4. 4 times 0 is 0. 2 to the 2 cubed is 8. 1 times 8 is 8. And then 1 times 16. Then you just add them together, which we get, what, 25? That's all there is to it. Now, they're only, in binary, there are only 2 glyphs, a 0 and a 1. So I can't put any other digit there. I provide all this as introduction because it's very easy to manipulate numbers binary numbers, since that's kind of what underlies everything, all data that's stored in computers. So when I say, and I'm going to use unsigned, I'm going to specifically use the word unsigned. Don't get hung up on that. That just simply means that there are no negative numbers. They just start at 0 and march on up. Okay, it makes things a little bit more sane as I move forward. So I'm going to call this num, so it's just an integer, and I'm going to make it 25. And internally, that integer should be a bunch of zeros. If I was to crack it open and look at the bits, it should be a bunch of zeros, except there should be a 1 in these positions. And that's actually what occurs, right? All information stored in a computer is all the zeros and ones. It's the binary. This is what 25 is inside of the computer. And there are a couple operators that let us play around with that. And one of them is the one that's useful to us at the moment, is this operator. And I would call this bitwise AND. So 0 and 0 is equal to what? What do you think? 0. All right, yeah. You see, you're afraid I'm going to trick you. That's why you're hesitant to answer. I'm not trying to trick you. What's this one? Yeah, excuse me. Tricking myself. All right. I have to put the, I'll do it in separate steps. I'll call this answer. Or how about has 2 to the 0, has 2, has 2 squared, has 2 cubed. And what did I went up to the 4th. Okay. So I can say has 2 to the 0, I can find that out, but if I take my number and I AND it with, what number is equal to that bit? What base 10 number, what human number, if you were to walk up to someone on the street and say, hey, you want to know what that first bit is? It's either 0 or 1. That second bit is either 0 or 2. That third bit is either 0 or 4, yes? That fourth bit is either 0 or 8, and that fifth bit is either 0 or 16. And I could keep going. Because if I was picking this last number, the 16 as an example, if I was to somehow be able to get my binary magnifying glass and look at all the bits, they'd be all zeros, except for that fifth bit would be toggled to a 1. That is how we represent 16. So let's print them out. 2 to the 0 bit is set to as 2 to the 0. Because what is it, if I look at lines 24 through 27, it's going to be 0 in all cases unless they're both 1. And this first bit will be 1, the second bit will be 1, this third bit is 1, this fourth bit's 1, this fifth bit's 1, which means I'm only going to get a 1 if it's turned on in num. Let me bring this, let me actually print this out. I'll print it out right here. So I'll say cout. Cout. Yep. 1, 2, 3. Where did I went up? 4. 4. 4, 3, 2, 1. Let me come over here. I don't like it bleeding over. I know that screws up the CCOD type, so let me do it this way. Right. Well, maybe I can even get rid of that one. There you go. There. Oh, right. This is showing 8 and 16. That's just showing that those are on. Those bits are on. Right. The one bit is on. The first bit is on. The fourth bit is on, and the fifth bit is on, which corresponds to the first, fourth, and fifth bits being on here. Looks like there's an older compiler on there. All right, I'll fix that right at the end of class. Yeah. Where did they get turned on and off? It is intrinsic in the number itself. So on line 31, by virtue of me assigning 25 to num, what you have to get comfortable with is that num is taking up, I don't know, 4 to 8 bytes of memory. Let's just say 4 bytes. They're 32 bits. Okay, and some of those bits have to be on, and some of those bits have to be off to represent the number 25. And it has to be the way it's laid out is the way we see it on lines 45 and 46. Those are the bits that have to be turned on to represent the number 25. And you can add them together. This is 1 plus 8 is 9, plus 16 is 25. So what I'm doing then is I'm just trying to show that literally these numbers are nothing but bits in the machine, and we can find out which bits are on and off by using that bitwise AND operator that I'm using on lines 38 through 42. What I'm doing on the technique that I'm doing on lines 38 through 42 is often referred to as a mask. So if you think of a mask in a traditional Halloween mask, what it does is it blocks everything and it just exposes certain parts of my face. What I'm doing on, say, line 42 is I'm blocking everything and I'm leaving a hole. I'm opening up to see what's there at the 5th bit. And that 5th bit is either going to be on or off. If it's on, then with bitwise AND, they both have to be on for that to end up being a number, and it is. It's 16. If it's off, then it ends up being 0. Yeah.
So if it's 32 bit, but then in the 0.
I'm sorry. 30. Oh yeah. 32 bits. So on. Right, so 32 bits ends up being 4 8-bit bytes. All bytes have 8 bits. So there are 32 bits, and they're all zeros except for the ones at the end.
So if you have a number that is larger than 2 to 7, how do you?
Well, that's only 8 of the 32 bits, so it would go 2 to the 8th, 2 to the 9th, 2 to the 10th, up to 2 to the 31st. Now on this machine, it's probably not for that. That'd be an older machine that had 32 bits. It's probably 64 bits. So for integers, you can represent a pretty darn large number, right? Yeah. Line 46.
Yeah.
I just wanted a blank line. If you look at on the left-hand pane, you'll see there after my 11001, there's actually, let me just drag it and you'll see if it'll let me drag it. Hang on. You'll see that right here there's a blank line. That's all I was doing. I was just creating some additional white space there. I wanted to do a blank line. If I remove it, I get rid of it, I compile, I run it. You'll see now that this line is actually right after this line rather than having a blank line there. So I was just adding additional space. All right, so this binary stuff we will deal with. I was thinking of doing something with the combination of the unordered map and the bit stuff on Friday's assignment. So I think that's where we'll take a closer look at that. Otherwise, we'll see you in lab.